Now we need to talk more about figures in 3D space. So we start off with the concept of lines and planes. When we started the semester, we were talking about things that were fairly similar between 2D and 3D. In that, we just add an extra z component to the distance formula or the midpoint formula or even the equation of the sphere from the circle formula. But there are some things that are very different, and lines are one of those things. And so we want to talk about lines in 3D space. And so your standard equation of your line, which is ax plus by plus c equals 0. Or sometimes we say equals c, depends on where you want to put the c. That's your standard equation of your line. And this is a linear equation in two variables in that, the x and y are first power, a, b, and c are constants. So you'd see something like 3x plus 4y plus 5 equals 0. All right. So you should know that from your algebra time. But you could also have your slope-intercept form, y equals, 7x minus 28. Slope-intercept form, but generally, same idea. But standard form looks like that. Now, what we can't do is we can't just throw a z into this formula and think that, okay, now we still have a line. Because it actually doesn't work. That doesn't give you a line. What we're going to see is that actually is going to give you a plane. So to talk about lines in 3D space, what we really have to do is parametrize that line. And so the way we do that is with a set of parametric equations. And so we need to know a little bit about parametric equations, and you can go back and review the basic concept of parametric equations that you should have learned in Calc 2. But we're going to use a set of parametric equations to define our line as opposed to a single equation to define our line. And we can actually do this in both 2D and 3D space. So it actually can go for both dimensional spaces. But we really need it for 3D space. Now, remember when we were in 2 dimensions, when we were talking about a line, in order to write the equation of a line, you needed two things. You need to know a point on that line, and you need to know the slope of the line. And if you knew those two things, we primarily use the point slope formula, which is y minus y1 equals m times x minus x1, which you used a ton in Calc 1 when you're writing the equation of the tangent line. And so to write the equation of a line in 3D space, we need something fairly similar to that. We need a point on the line. So we're going to be given a point on the line, but that now is going to be a 3D point. Okay? So the coordinates are going to be x1, y1, z1. And we need the slope, but we don't really have the slope, and we haven't talked about what the slope means in 3 dimensions or anything like that. So what we're going to do instead is we need a vector, say v, so it's a 3-dimensional vector, coordinates or components are a, b, and c, that's parallel to our line. All right. So again, here's the idea. This is a line. That's the line we're trying to write the equation of. We need a point on that line, say point P, that has coordinates x1, y1, z1. And we need a vector that's parallel to that line, and that vector would be vector A, B, C. All right. So if we have these two things, we can find the equation of this line, and this vector parallel is acting essentially like the slope of the line, all right, that we would have had in 2 dimensions. All right, so what we're going to do is this. We're going to come up with another point on the line, and there's infinitely many points on this line, but we're going to call this other point Q. And we don't know what the coordinates are, but the coordinates have an x, a y, and a z component, so we'll just call it Q, x, y, z. All right. And what we can do is we can find the vector between P and Q. So we can find vector PQ. Okay? And vector PQ would essentially be x minus x1, y minus y1, z minus z1. So we do terminal minus initial. So it would look like this. All right. And vector PQ should be parallel to vector v. Why? Because PQ is on the line and v is parallel to the line, so PQ should be parallel to v. Well, if PQ is parallel to v, okay, then they're pointing in the same direction, which means the only real difference between these two vectors is their magnitudes. So one can be considered a multiple of the other. You know, when two vectors are parallel, the only difference between them would be their magnitudes, and the way you change the magnitude of a vector is by multiplying it by some constant multiple. So we could say that vector PQ is equal to some multiple t times v, where t is just some real number, right? And so here, this arrow is going a little too far here, so it should just be over PQ. But anyway, if that's the case, then vector PQ, which we said was this, should be equal to t times v. Well, t times v should be t times a, t times b, t times c. So these should equal each other. Well, if these equal each other, then the first component of each one of these vectors should equal the second component of each one of these vectors, and the third component of each one of these vectors should equal each other if the two vectors equal each other. All right. Well, that being said, what that tells us is that x minus x1 should equal at, y minus y1 should equal bt, and z minus z1 should equal ct, which we can actually rewrite as x equals x1 plus at, y equals y1 plus bt, and z equals z1 plus ct, which would essentially say that any x1, y1, z1, and abc that satisfy these sets of equations would create the x, y's, and z's that make up our line. So what this is the set of parametric equations that give us our line. And what you should know about parametric equations is basically the way they work is that you define your variables x, y, and in this case z in terms of another variable, in this case t, often represented in time, but not necessarily. But here, x is basically a function of t, y is a function of t, z is a function of t. Because remember, x1, y1, z1 come from the point P, which means they're just constants. And a, b, and c come from the vector v, which means they're just constants. So t is the variable here. So z is in terms of t, y is in terms of t, x is in terms of t. That's your set of parametric equations that define your line L. And any x, y, z that satisfies these equations are the x, y's, and z's that are on the line L. Remember, Q was just this random point. You know, we had this P and we had this Q. Q was just this random point. All the points x, y, and z that could make up this Q, which could be here, 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 and here, are all the x, y's, and z's that make up my line. So, based off of what we just discussed, a line L parallel to the vector v denoted by the coordinates a, b, c, the components I should say, a, b, c, and passing through the point P, which has coordinates. Oh, I got some major problems here. This should be parentheses, is represented by the parametric equations x equals x1 plus at, y equals y1 plus bt, z equals z1 plus ct. Another way to do this is what we call a vector parametrization, which will not make much sense to you right now. This is the whole next chapter concept of something called this vector parametrization. And so this will make more sense later, but just thinking about this here on the right-hand side. Ignore this. What do you see here? You see a vector plus a constant multiple times a vector. And so this is basic operations that we just got done talking about in previous lessons, where we would distribute this in here, okay? And everything would be multiplied by t. And then if we add the two vectors together, you add the components, so you would get x1 plus at, y1 plus bt, and z1 plus ct as the three components to a vector, right? And it's still a vector because vector plus vector gives you vector. And those are exactly these three equations in our parametric equations. Other than that, I'm not going any further with the vector parametrization. We'll get back into that in the next chapter. Another thing you'll see, though, here is this thing called symmetric equations. So my preferred way of writing the equation of a line is with the three separate parametric equations, or eventually this parametrization. But another way we can do it is with this, what we call symmetric equations. And rather than solving each equation for x, y, and z, we can solve each equation for t. But the t in this equation is still the same t, and this equation is still the same t in this equation. Those are all the exact same t. So if you solve each one for t, you should be able to set them equal to each other. So everything here equals t, and that's where we get the symmetric equations. Again, my preference, the parametric equations. All right, so simple question. Find the parametric, and we'll also do the symmetric, equations of the line L that pass through the point 2, 1, negative 3, and is parallel to the vector negative 1, negative 5, 4. All right, so pretty simple. We're going to use the formula that x equals x1 plus at, y equals y1 plus bt, z equals z1 plus ct. Those are our three parametric equations. This is x1, y1, z1, and this is a, b, c. Simply put them in, and we get the three parametric equations. X equals 2 minus 1t, y equals 1 minus 5t, and z equals negative 3 plus 4t. That's it. If you want to solve these for t and do the same thing, the symmetric equations would be x minus 2 over negative 1 equals y minus 1 over negative 5 equals z minus negative 3, so plus 3 over 4. And that would be your symmetric equations here. Again, they equal t. This is my preference. That's it. Pretty simple. But it's not always that simple. You've seen questions where you had to write the equation of a line. Not everything is necessarily spelled out for you in terms of what you need to write that equation, so it's a little bit more work. This question here kind of goes along with that idea, in that we want to find the set of parametric equations for the line that passes through this point and also this point. What we need is a point and a vector parallel to the line. Well, we have 2 points and no vectors. So how are we going to write the equation line, right? Well, we need the vector. So think about it. We have a line, let's say L. We have a point and another point. We know both of these points. Let's call this P, let's call this Q. So here's P, here's Q. It doesn't really matter what the orientation is. They're both on the line. So what we need to do is come up with a vector, V, that's parallel to this line, knowing this information. Well, the easiest way to do that is to find the vector between P and Q. And it doesn't matter whether it's the vector PQ or the vector QP. Either way, that vector, since it's on the line, is parallel to the line and will be the parallel vector we're looking for. So let's just find vector PQ, in which case we will do terminal minus initial, so 5 minus negative 3, 4 minus 1, and negative 6 minus negative 2. And so we get, 8, 3, and negative 4. Okay? So there's PQ. If you did QP, you would get the same thing, just a negative of each one. So this is our parallel vector. Okay, this is the parallel vector. All right, so that's our A, B, C in our parametric equations. Now we need a point. We have 2 of them, so pick one. It doesn't matter. I'm going to pick this one. If you could pick Q, your equations will look a little different, but that doesn't mean you get a different line. You would still get the same line, just the equations would look slightly different. They would still yield the same points that would make up the line. So here's our parametric equations. X equals, let's say, -3 plus 8t. Y equals 1 plus 3t. And z equals -2 minus 4t. If I chose to use the other point, I would get x equals 5 plus 8t, y equals 4 plus 3t, and z equals -6 minus 4t. Now they may look like a different set of parametric equations, but in the end, when I plug in different t values and I create my points x, y, and z, I would get the same exact line. Very similar to this idea of, let me get some space here, of looking at a line and let's saying, I don't know, x plus y equals 7, or 2x plus 2y equals 14. These may look like two different equations, but you know that this is just a multiple of this, and therefore they're the same line. They still have the same solutions, same idea. Okay? So, doesn't matter how you find the vector PQ, QP, doesn't matter which point you choose, but you do need that vector parallel, and that's how you would find it. Okay, now we want to find the equation of a plane. And now we talked about, if we look at just this linear equation, this is the equation of a line in 2D space, and we try and throw a z onto it. So I don't know, ax plus by plus cz equals, say, d. We don't get a line, but what we do get is something that is still kind of linear in nature, and what we end up getting is a plane. So this is the 2D equation of a line. This is the 3D equation of a plane. And we're going to see where that comes from. All right, so the idea is this. I see an issue real quick. This should be sub 1, sub 1, sub 1. Okay, those should be subscripts. So, just like a line, we need some information about the plane to be able to write the equation. And what we need is a point. Okay, we need a point. Oops, wrong color. I don't want to black that out. Highlight it. We need a point in the plane and a vector, but in this case we need a vector normal, so meeting at a 90-degree angle, perpendicular to the plane. And so if the plane contains this point, and this is x1, y1, z1, and having the normal vector, say n, be ABC, let's put a little arrow above that n, okay, then the plane is going to have to consist of all points Q such that PQ is orthogonal to n. What does that mean? All right, let's draw a little picture. There's our plane, okay? All right, so there's our plane sitting there, whatever that plane is. Here's this point P on the plane, and that point has an x1, a y1, and a z1. We know those points. And we have this normal vector to the plane. Let's call this n. And we know that meets the plane at a 90-degree angle, right? So we have that. We know that that is ABC. What I'm going to do is I'm going to create another point and say, okay, here's another point Q. Actually, there's a lot of other points Q that make up this plane, right? The plane is consistent of infinitely many points that all lie on this plane. But let's look at this point Q. And that Q has just a random x, y, and z coordinate. And let me find the vector PQ. Well, since PQ is on the plane, and n is normal to the plane, then n is orthogonal to PQ. Well, if it's orthogonal to PQ, then the dot product between n and PQ, it should have an arrow above it. I think it did it one time and it kind of copied off. But anyway, n, the dot product between n and PQ should be 0. Something we learned about dot product. Okay, well, what's PQ? Vector PQ should be x minus x1, y minus y1. Oops, too many commas there. Let's put a comma there. And then, comma, z minus z1. All right, that's vector PQ. And so the dot product between PQ and n should be 0. Well, here's n. Here's PQ. If I do their dot product, I do a times x minus x1 plus b times y minus y1, z times z minus z1. And that should equal 0. Well, all the x, y's, and z's, all the points q, whether it's here or here or here, that satisfy that equation should make up my plane. All the points q, so that when I connect PQ together and I create another vector that's normal or orthogonal to this vector, should make up all the points on my plane. So there's your equation of a plane. We'll look at it a little bit closer. So the standard equation of a plane in space is a plane that contains the points x1, y1, z1. So that point's on the plane, and having normal vector n, abc, can be represented in standard form using this equation we just came up with. But we can also look at what we call general form. So if we distribute this a into here, and b in, and c in, what you're going to see is a times x will give you ax, and a times x1 is just a constant, because a and x1 are both constants. So that's a constant. B times y, okay. But b times y1, again, is a constant. And c times z, and c times z1 is a constant. Okay, equals 0. Well, if these are all constants, then I can just call this one big constant, say d. I can move it around no matter where I want because it's a constant. And I can write this as ax plus by plus cz, say, equals d. Well, in that case, this is negative d, so d moves to the other side. Now it's d. But that's what we're going to call the general form of our plane, which, if I took the cz away, that's the equation of a line in two-dimensional space. With the cz, that's the equation of a plane in three-dimensional space. So just increasing the variables to throw a z into the mix was why we don't do that to write the equation of a line. That's why we have to do the parametrization to write the equation of a line. Because when you throw a z into the linear equation from 2 dimensions, you don't get a line, you get a plane. So that's something to note. All right, so if we just do a simple equation, simple question, I should say, that says, find the equation of the plane that goes through this point and has this normal vector. It's very simple. Just plug everything into where you need to here, and you got your answer. So this is a, b, c. This is x1, y1, z1. And so we would say we get negative 2 times x minus 1 plus 5 times y minus 2 minus 6 times z minus 3 equals 0. That's it. And I don't care if you write the standard form or the general form. If we wrote the general form, we'd have minus 2x plus 5y minus 6z equals, what would we get? This would be 2 minus 10, so it's negative 8, plus 18, so that would be 10. Move to the other side, so minus 10. So there you go. Yeah, here I have it as the d on the same side, so let's correct that. Plus 10 equals 0. That's fine too. Okay, so there you go. There is your general form of your plane in 3D space. One thing to note is you need to start becoming more and more familiar with equations and what they look like geometrically. And so when you see something like this, you need to recognize that this is a plane. X, Y, Z, all to the first power. When you would just see X and Y, you would think line. Now you see X, Y, and Z to the first power. Now you got to think plane. Not only that, you got to realize that the coefficients in front of X, Y, and Z are the components of the normal vector. You can just stare at this equation and automatically get that information. So something you got to be aware of. This question takes all that and kind of makes it a little bit more difficult because it doesn't give you everything you want to write the equation of the plane. So we want to find the equation of the plane. That plane passes through these 3 points. So we have this plane here. And something to note, when I draw a plane, I draw it as having edges, right? Here's an edge, here's an edge, here's an edge, here's an edge. But planes don't really have edges to them. Planes go on forever, infinitely, in all directions. We draw it as having these edges so that we can sort of visualize a little bit better, like a piece of paper. But think of like an infinite piece of paper. You know, that's essentially what your plane would be. It doesn't stop. It doesn't have an edge. It just keeps going and going and going in all directions, but it has that sort of flat quality to it. So anyway, we have these 3 points that are all sitting on this plane. And we want to find the equation of the plane that consists of all 3 of these points. Now, how are we going to do that? Remember, what do we need? We only need one of these points, and we need what we call the normal vector. But that's what's missing. We don't have that normal vector. So how can we use the 3 points to get the normal vector? Once we figure that out, we have what we need. Well, let's call this one P, let's call this one Q, let's call this one R. I can find vector PQ. I can find vector PR. And I would need to use those to come up with N. Well, just think about it. If PQ is on the plane and PR is on the plane, how would we get the vector normal to the plane? Well, we need the vector that's perpendicular to both PQ and PR. Well, that should be the cross product between PQ and PR. So let's call this P, Q, and R. So vector PQ would be terminal minus initial. So 1 minus -1, so +1, and then 3 minus 2, and what's that going to be? -1 minus 4. So what do we get? 2, 1, -5. And then vector PR would be what? 2 minus 1 is 1. 2 minus -1. Ooh, do that right. 2 minus -1 is 3. -3 minus 2 is -5. And 1 minus 4 is -3. So look at these 2 vectors. These are vectors you're going to do the cross product of. So if we're going to try and find N, we want to do I, J, K. Use a different color here so I can see it. Let's go 2, 1, -5, and 3, -5, -3. Let's think for a second. Order here doesn't really make too much of a difference. I set up these vectors randomly. I assigned the points randomly. If I did vector PQ, and let's say I did vector RP, and I found the cross product between RP and PQ, I would still be finding a normal vector to the plane. Or if I did RQ and RP, I'd still be finding the cross product would still be normal to the plane. And so the order in which I created these vectors doesn't really matter. Also, the cross product, whether I do PQ cross PR or PR cross PQ, it'll give me that vector or it'll give me that vector that's still normal to the plane. It's just pointing in the opposite direction. So it doesn't really matter what kind of order we do this in. We kind of can't mess this up order-wise. Now you can mess it up computationally, but just think about that. So anyway, so let's do the I component. So we're here. And so that first component would be, I'm going to write it in bracket notation, so this minus this. So -3 minus 25. Then we have negative of the second component, which is this one and this one. So we get -6 minus -15. Okay, and then the third component, we use these. So that would be -10. What would it be? -10 minus 3. That's the third component. That's the K. So our normal vector would give us, what, negative 28. This would become plus here, so negative 6 plus 15 would give me a 9, and then the extra negative, so negative 9. And then we would get negative 13. Let's double check that one more time, because we need to make sure that that's right to do the next step. So again, I would be negative 3 minus 25, so that's right. J would be negative 6, and this is a negative 5, right? Yeah, it's a negative 5. So that would be negative 15. We subtract it, and then we subtract the whole thing. So yeah, that's right. And then we have the negative 13. So negative 10 minus 3. Yeah, okay. So that's your normal vector. So if that's your normal vector, pick any one of these points as your point on the plane. Let's go with this one. And my plane will look like this. Negative 28 times x plus 1 minus 9 times y minus 2. Minus 13 times z minus 4 equals 0. This is my x1, y1, z1. This is my ABC. I use the standard equation, and I got that. Done. All right, a few more things with planes. We can wrap this up. First off, two planes are parallel if and only if their normal vectors are parallel, so they'd be scalar vectors of each other. Think about that. Pretty easy idea. Here's one plane, here's another plane. If they were parallel, we look at this normal vector, we look at this normal vector, and these two vectors should definitely be parallel to each other, and vectors that are parallel, one's a multiple of the other because their directions are pointing in the same way. So the only difference between this and this would be their magnitudes. And to change the magnitude of one vector to another is to multiply it by a scalar. So that's important. If two vectors are not parallel to each other, then they would have to intersect. And the idea here is that if you look at these two planes, they would intersect at this line right here. So two planes intersect in a line. That would be the intersection of two planes. We could find the angle between two planes by basically looking at the angle between their normal vectors, and that's what this formula would be. So if I had normal vector there, let's say n1, and I had normal vector here, let's say that's n2, and I kind of move them, so now I'm going to move this to here and still make it parallel to the original one. That angle should be representative of that angle. And my picture's not great because I don't really have 90 degrees on each one, but nonetheless, that's the idea. And if the normal vector's dot product is 0, then those two planes meet at a 90-degree angle. So the two planes are orthogonal to one another. So here's a quick question. Find the angle between these two planes. Okay? After we do that, then we'll look at the line of intersection. So let's look at the angle between the planes. Well, in order to find the angle between the planes, we need the normal vector. So let's call this plane 1, and this is plane 2. So that's plane 1, and that's plane 2. All right. Plane 1 has normal vector n1. Plane 2 has normal vector n2. How do we find the normal vector? Remember, the normal vector is just the coefficients in front of x, y, and z. So n1 is 1, negative 2, 1. It's the ABC. Okay? And n2 would be 2, 3, negative 2. So those are the two normal vectors. So then to find the angle between those normal vectors would then give me the angle between the planes. And so that's pretty simple to do, in that we do the cosine of theta equals the dot product. So that would be what? 3 minus 6 minus 2 over the magnitude of n, which will give me the square root of 1 plus 4 plus 1. And then the square root of n2 would be 4 plus 9 plus 4. So theta equals the arc cosine of, what's that, negative 8 plus 3, so that's negative 5, over square root of 6, square root of 17. Right? And, that doesn't really tell you a whole lot, in terms of the angle. You have to then figure out what this angle is. Knowing that you're taking the arc cosine of a negative, you should at least know that theta has to be somewhere between pi halves and pi, from what you know about arc cosine. But to find the exact angle, your best thing to do would be to plug this into your calculator and get the degree measurement off of that. But nonetheless, this is a perfectly fine answer. What you can tell is that it's definitely not, the dot product isn't 0 and the angle isn't pi halves. What you can also tell is that, you don't want the angle to be 0, right? You think about cosine of 0 equals what? Well, cosine of 0 equals 1. So the idea here is you don't want this to be 1, because the arc cosine of 1 equals 0. So clearly that doesn't happen. Why would we want that? Well, because that would tell us that the two planes are parallel to each other. The angle between them is 0. So we know the angle is not 0. We know it's some angle between between pi halves and pi. Other than that, we don't really need to go any further in detail than this. This is fine. So that means that they're going to intersect. All right, so if they're going to intersect, then we want to find the equation of the line for that intersection. Well, it's a 3D line, so we have to have the parametric equations for that line of intersection. Well, what do we need? What we need is we need a point on that line, and we need a vector parallel to that line. Okay? Well, that vector that's parallel to that line should be on this plane and on this plane at the same time, right? If you think about it, if it's parallel to the line, it could just be on the line. That line is on both planes simultaneously. Well, if it's on both planes simultaneously, it's perpendicular to both normal vectors simultaneously. Well, how are we going to find the vector that's orthogonal to both n1 and n2 at the same time? Well, we'll do that through the cross product. So we need that. That'll give us our vector parallel. That's parallel to the line. All right. And then we need a point on the line. Well, we need to find a point, x, y, and z, that satisfies this equation and simultaneously satisfies this equation. So it satisfies both equations at the same time. Here's a cheat for this example. The cheat for this example is that both of these are equal to 0. And since both of them are equal to 0, clearly if x, y, and z were all 0, that would satisfy this equation. And it would also satisfy this equation. So 0, 0, 0 is on this plane, and it's also on that plane. That's a cheat for this example. What if this one was 3 and this one was 0 as far as what it's equal to? Now 0, 0, 0 does not satisfy this equation, so we're out of luck. How would you do it? Well, the way you would do it is solve a system of equations. The problem is we have more variables than we have equations, and that makes things a little bit difficult, which all that tells us is there's not a unique solution. There's not one solution. There's infinitely many. They make up this line, essentially. And so the idea here is I'm just going to plug in something random for z. I like to plug in 0 for z here and here. So the coordinate here would be 0. And then I'll solve the resulting system with 2 variables in it. Using my basic algebra, here's 2 variables, 2 equations. Let's solve that, and we'll find the x's and y's that go along with this particular z. We don't need to go through all that for this equation because we can clearly see 0, 0, 0 is going to work. But what we do need is the cross product. So for the cross product, I'm going to need I, J, K, and 1, negative 1, 2, 1, 2, 3, negative 2. Then I'm going to get what? This times this, or sorry, this minus this. So 4 minus 3, so 1. Then the negative of this one and this one, so it's at negative 2 minus 2, so negative 4, so plus 4. And then the last one would be 3 minus negative 4, so 3 plus 4, so 7. So there's your normal vector. All right, there's your point. So now, if I can erase some of this, I can write the plane, or sorry, the equation of the line. That's what we're doing here, as x equals 0 plus 1t, y equals 0 plus 4t, and z equals 0 plus 7t. And that would be the set of parametric equations that describe the line of intersection, using this point that's on that line and this vector that's parallel to that line. This basically takes into account everything we've discussed over the past couple of lessons.